Okay. One thing I meant to mention last week when we talked about spectroscopy and how chemical elements and compounds have signatures because they emit certain definite wavelengths of light. Well, this is how fireworks work. Okay, if you ever wondered, how they can shoot things up and have them explode in all these fabulous colors, it's in the explosive. They put certain chemicals. When you see a burst of yellow, okay, that's sodium. You're looking at the sodium line, the yellow line from the sodium. And let me see, I actually looked up on the internet fireworks this morning, and they list the various chemicals that they use that give rise to the colors that you see. Blue is copper chloride. Green is barium chloride. Orange is calcium chloride. So they pick chemicals that emit really strongly in a certain wavelength that's orange or blue or red, and that's they're using that principle to create the fireworks. Okay, this morning we're going to do our last class on chemistry. There's one before we get back to some physics to fill out the rest of the year. But the last thing I wanted to tell you about chemistry was how chemists started making progress on another topic that was originally thought to be unknowable. We talked about one of these topics last week, where this philosopher Comte actually gave as his example of something obviously unknowable what the stars were made out of. And then we saw exactly how scientists actually figured out what the stars were made out of. Because of these signatures from the elements, they emit certain wavelengths of light. Well, another topic that had been regarded as unknowable is, most scientists in the early part of the 19th century thought, well, even if you accept this idea of atoms, and it helps explain some things like Dalton's law of multiple proportions and Avogadro's law and so on, we can never know how the atoms are actually arranged in molecules because it's just too remote from what we can ever directly perceive. Basically, it was the same reason that they gave for why you could never know what the stars were made out of. You can't go to a star and collect some material and then bring it back to your lab and analyze it. It's just so remote, we could never know that. Well, and then they found this property of light emission that told them the answer. Well, it's the same thing with these very small molecules. How could you actually know how the atoms were arranged in the molecule? Well, it was around the middle part of the century that scientists actually started figuring out how the molecules had to be arranged in order to give a consistent picture with everything they knew, in particular using this concept of valence and the chemical properties of the element. They could actually figure out how the atoms had to be arranged in the molecule. And let me give you some of the early examples. So the first guy I want to tell you about here is, let's see. Friedrich Kekula. And the discovery I'm going to tell you about he made in 1858. There was a liquid that you can get from coal. Turns out that coal, it's mostly carbon, coal is, but it's not all carbon. The coal that you find in nature, if you take it and you heat it up, you'll boil off some material that people called coal tar. And the coal tar, if you have 1,000 pounds of coal, you can actually get out of it about a pound of a liquid that they call benzene. Okay, so now, when chemists analyzed this liquid, benzene, they found that the molecular formula was it had equal numbers of carbon and hydrogen atoms. It actually had 6 each. Now, does that seem surprising to anyone? Neve?
Why isn't it just one carbon and one hydrogen?
Oh, that's a good question. Yeah, I actually just thought of that question before you asked it. How they figured out there were 6 carbons and 6 hydrogens, I'm actually not sure. Maybe Kekula actually didn't know that at the beginning. He just knew it was a one-to-one relationship. And when he figured out the molecular structure, he realized that it had to be 6s. I'm actually not too sure about that. But yeah, it's a good question. But yeah, I suspect that's the way it went. That I've already given away part of the answer here by writing these 6s. I should have held off on that. That all they knew at first was equal numbers of carbon and hydrogen atoms. Now, that's kind of surprising, though, because, for instance, one of the common natural gases that I've told you about, methane, is 1 carbon to 4 hydrogens, right? So, and we know that carbon has a valence of 4. Okay, so it has 4 hooks, basically, where it can attach to other atoms. Now, how can you have a compound that has equal numbers of hydrogens and carbons and yet make use of these 4 hooks that carbon has? That's right.
Carbon could be hooking to itself, like using a lot of hooks.
Right, to hook to the other carbons. Okay, that has to be the case, because we know that the hydrogens only have 1 hook each. But it's still a mystery. Now, how exactly do you work this out? Now, Kekula was racking his brain about this for a while, and he claims that his breakthrough came when he had a dream. And in his dream, he pictured snakes that wrapped around and were biting their own tails. Now, does that give you any clues?
Snake venom? It's a circle.
It's a circle. Okay, let's see what we can do with that idea. So let's let me see. Now you can try different numbers of carbons in the circles, but I'm going to skip right to the one that works here. Now, we know that each hydrogen just has the one hook. So let's hook up a hydrogen to each of these carbons. Now, does that work?
Don't each of the carbons still have one hook left?
Yep. We're still missing an extra bond for a carbon. Yeah.
Could the opposite carbons attach to each other?
Oh, you could do this. It turns out it doesn't work that way. But there was one thing I told you when we talked about carbon dioxide. Yeah, that's right. Yeah, double hooking. The carbon is capable of forming these double bonds. So what Kekule realized was, well, here's what must be going on. If we have something like that, now that explains, yeah.
How can you tell which one is a double?
Oh, he can't. I mean, I could have easily drawn this just the other way, right? That where the ones that I have as singles right now become doubles, and the others become singles. But it's the same. It's the same compound, right? So basically, all you know is that every other one is single and every other one is double. Now, turns out that this is the only structure that that Kekule could come up with that would have equal numbers of hydrogens and carbons and have be consistent with the fact that carbon has a valence of 4 and hydrogen has a valence of 1, and be consistent with all the chemical properties that were known of benzene. So this, he had actually figured out starting from observational data and seeing patterns and seeing having these ideas of valence at his disposal, he could actually figure out what the molecular structure of this rather complicated compound had to be. Now, it turns out benzene actually is a pretty important chemical. Chemists would be devastated if you took benzene away from them because there's a lot of these cyclic compounds in organic chemistry and the chemicals that are in our bodies. And the way that chemists make those compounds is basically by starting with benzene and then adding things to it. So it's a really important compound in chemistry, and the molecular structure was figured out in 1858. Now, you can, like I said, you can do a lot with this compound. You can, it undergoes a bunch of different reactions depending on what you put it with, and the reactions typically consist of substituting for one or more of these hydrogen atoms. For instance, if you can take you can react benzene with bromine, which is another compound that has a valence 1, okay, that's in that group. And say you can substitute for one of the hydrogens, a bromine atom. Now, you can do this kind of substitution, more than once. So you can put a second bromine atom on one of these benzene molecules. Now there's several different places it can go, right? You could put the bromine here. What are the other places you could put it that would try? Yeah. Now you could. Well, let me put it this way. If you're talking, this compound here would be called I think they call it dibromobenzene. Okay, which is reasonable name. You can sort of tell by the name what's happened. Di means two. You've substituted two bromines for the hydrogens. Now, how many versions of dibromobenzene would you expect there to be? Yes. 5. Okay. Let me just call this section I'm starting into here explanation of isomers. Let's see, example 1, dibromobenzene. Okay, now
Would there be 30 different ones?
30.
Because,
No, they'd be less because they can repeat.
oh, right.
Daniel?
Wait, see, I think it's 36 because it can be on any one of those 6,
Yeah.
and then the other one can. Oh no, it's 1/6 times. It's 30.
Okay.
If it's one up there, the other one can come off into the other 5.
Okay, but to see that that's wrong, here, consider a simpler case. Let me go back to just the benzene where you have one bromine that's substituted. How many different cases are there in this one? Hmm? 6. Are those 6 distinguishable? I mean, what if I take, is this a different molecular structure than that? No, all you have to do is rotate it. It's the same thing.
Yeah, there's 2 on that side. There's 2.
Oh, yeah, no.
But there's 2 on the one side, so if you rotate it, you have 2 on top, 2 on the bottom, and 1 on the sides. Is the way you
Oh, okay, maybe I didn't draw this perfectly. This is a completely symmetrical ring, okay? So basically, no matter where you put the 1, it's the same thing. I mean, all you've done is rotate the molecule, basically. Yeah.
There are 3 combinations.
Yeah, exactly. Neve just, okay, so once you see that it's not different, if you can rotate the molecule and make it look like the other one, then it's not different. So if you have two now, so the mono bromobenzene has no isomers at all. It's just monobromobenzene. There's just one of them. If you have two now, as soon as you introduce the second bromine atom, now you're going to have isomers, right? Because putting it adjacent to the bromine that was already on there is different than putting it on the opposite side, for instance. So, but Neve actually came up with the right number. There have to be 3 of these isomers now, distinguishable molecular structures, because you can put the second bromine atom right next to the first one, or you can put it 2 slots away, or you can put it 3 slots away. So there's let me draw all 3. You can have that. You can have that. And then finally you can have, so you have the arrangement where the bromine atoms are adjacent. You can have them when they're separated, but with one carbon with one hydrogen carbon pair in between, or you can have them on opposite sides of the ring. So there's 3 different arrangements. Lo and behold, when chemists actually they investigated the properties of these bromobenzenes, they found that there were 3 distinguishable compounds with slightly different properties. Troy.
About the one where, the case where there's only one bromine,
Yeah.
especially with the hydrogen, couldn't there be 2 because one on one side was a double hook and on the other side was a
Yeah.
single hook?
Yeah. Good. Excellent question. It's a little tricky to answer. It turns out that these hooks that I've been talking like they're mechanical hooks, they're not exactly. They're a little more complicated than that. And what's actually happening in a real benzene ring is you don't have the double bond, always on this side and this always being a single bond. What's happening is it's constantly flipping back and forth between the two. So these bonds are not stable in that sense, so what you actually have is this bond is sometimes double and sometimes single. This one's sometimes double and sometimes single. So it's when you finally get to a real in-depth study of chemistry, particularly organic chemistry, you'll learn all the complicated details about these bonds. That's a whole subject in itself. We're going to get part of the way there in this course, where I'm actually going to tell you a little bit about the structure of atoms during the next month, that will at least allow us to get started in understanding what these chemical bonds are. Okay, so the bottom line is it doesn't give rise to those two structures that. Okay, so, but now when chemists actually, I mean, you might think, well, is this real, or are chemists, just playing games with these structures, and seeing how many different structures they can dream up and draw on paper? Well, it added a lot of reality to it, a lot of evidence for this molecular structure when chemists actually went out and found that for dibromobenzene, there were 3 isomers. So, which is what you get just by playing around and drawing these diagrams. Okay, now let me see. Let's do. What if I change this, just to test you here? What if we do tribromobenzene? How many different isomers can we get, Nick? 3. All right, let's see. That's 1, right? Let me see. Here's 1. And oh, wait a minute. There's 1, right? Okay, I think that's it, isn't it?
No.
Does you see another one?
One in that corner and one in that.
One there.
Oh, but that's the same as this one, isn't it? Because 2 of them are adjacent. Oh, you're saying no, that's the same. It's the same because see, on this one, it doesn't matter whether this bromine is here or here, right? That's just, you can get, by rotation, you can make one equivalent to the other. So yeah, it's just those 3. So you also get 3 for tribromobenzene. Yeah.
Is it 3 for the next one too? Or?
Oh, if you put 4 on there, yeah, actually it would be 3, right? It's exactly, yeah. It's not a general principle, by the way, that there have to be 3. It's just the way it worked out in this case. But you can see that by starting to discover these molecular structures, chemists are suddenly in a position of being able to predict the number of isomers that they're going to find in any given compound, and they couldn't do that before. So this is the idea of atoms, and in particular the discovery of molecular structure, is giving them a predictive power that they never had before. But there were problems, and so let me tell you about some of the problems. Here, let me just call this problem case. if you take, well, I mentioned methane gas earlier, where you have a single carbon and you have 4 hydrogens. Well, in that case, you can take methane and react it with chlorine gas and substitute for some of those hydrogens chlorine atoms. And in particular, one of the gases you can create by doing that is a gas that has, again, the single carbon, but you've substituted for 2 of the hydrogen atoms a chlorine atom. So you have now 2 hydrogen atoms and 2 chlorine atoms attached to the carbon. Now, what would you predict for isomers in this case? So let's just do it the same way we did it for the benzene. There's one way you could have it, right?
I thought chlorine only had 3 attached. Or not chlorine, but carbon only had 3.
Oh, no, it has 4. But there was, like in the benzene case, there were the double bonds that made it, that made it add up to 4. Here they're all single bonds. Troy.
There's just 2.
Troy says 2. Okay. So I can guess what Troy wants me to do here. That, right? Okay, so we seem to have 2 distinguishable cases here. One where the chlorines are on the opposite side of the carbon, and one where the chlorines are adjacent. So we ought to have 2 isomers. Well, chemists can easily make this gas and see whether or not it displays any inconsistent chemical properties. In other words, that it seems like a mixture rather than a pure gas. Look for whether there are 2 different isomers. And they do that. No. It all seems to be the same stuff. They don't see any evidence for two different isomers here. Now, anybody that figures this one out gets an automatic A in the class. But there's something we're overlooking here. It's these 2 cases seem pretty clearly different. But we're overlooking something really basic, which is sometimes happens to scientists. What's the difference between these drawings I'm making on the board and real molecules? Neve.
They have certain sizes and
Yeah, you're on the right track.
have to work with the structure.
Yeah, what does it mean to have a size? I mean, I could say that this drawing of mine has a size. Right. 3-dimensional. Yes, exactly. The problem with these diagrams on the board is they're 2-dimensional. Why would we expect real molecules to be 2-dimensional? I mean, they aren't. There's 3 dimensions around us. So if we have a carbon atom in the center and 4 atoms attached to it in 3 dimensions, what might that look like? Well, it turns out that there is a geometric figure that you may be aware of called a tetrahedron. Okay, evidently you aren't aware of it. But if a tetrahedron is and it's like a pyramid thing. Uh-oh. Now I'm at the limit of my artistic abilities. Let me... If you take a carbon atom and put it in the center, and you have 4 prongs coming out of it, you can arrange those 4 prongs so the ends of them are all equidistant from each other. Like I say, I'm not a very good artist, but that's called a tetrahedron. It has, and if you look at this solid shape, it has 1, 2, 3, 4 triangles that are all identical. It's like a little pyramid thing, but every corner of it is equidistant from every other corner. Now, if you put the carbon atom in the middle of that, it turns out that there's no, you can put 2 chlorines here. I mean, you can have, let's say the dark circles are the chlorines, and my empty circles are the hydrogens here. Well, no matter where you put 2 chlorines, you can rotate this thing to superimpose it on any other tetrahedron that has 2 chlorines. So as soon as chemists realized there was something fundamentally deficient about these little 2-dimensional diagrams that they were drawing, and they started thinking in terms of 3 dimensions, this was one of the problem cases that went away. They immediately saw, oh no, we shouldn't expect 2 different isomers here. It's all the same thing. Now, in order to really convince you of this, I think I would have to actually have 3-dimensional models.
We'll get a tetrahedron on Wednesday.
Okay. Okay. Okay, so that's the guy who figured this out was a chemist named Van't Hoff. In 1874. He was the one that started working with these 3-dimensional models and figured out that carbon atoms have this tetrahedron structure to their bonds. And that explains why, in some cases, chemists expected to find isomers that they didn't find, and in other cases, they didn't expect to find isomers that they did find. Now, let me give you I'm going to give you a couple more cases that Van't Hoff could explain that were mysteries before he introduced his 3-dimensional models for these molecular structures. Well, here's an interesting case. There's a chemical called lactic acid. Okay, it's in our bodies. It's actually, you know, when you, if you go out and exercise really hard, like I don't know whether you've ever tried to, like run around the track, you know, as hard and as far as you could, and at a certain point your muscles just lock up. And it's like you can't, it's like you're running underwater all of a sudden. You know, you can hardly move your legs. Well, that's due to lactic acid buildup in your muscle. So we got lactic acid in our bodies. But it turns out that this chemical comes in two different varieties that are very subtly different. And the only one that's operative in your body is one of these two different compounds. Let me just tell you what lactic acid is. It's a carbon with 4 different groups hanging off of it. Well, let me just call this. So this last group is a carbon, 2 oxygens, and a hydrogen.
O2.
Huh?
Can't just be O2.
Well, what this is a common group in organic chemistry, and the way it's actually structured is like that. Which I have to say that because otherwise Troy would ask me why it doesn't have 4 bonds. So it this is actually what I mean by this. Okay, but well, we're at the end of our time here, but I'll tell you why you can get 2 different compounds out of this that are subtly different this afternoon.